Here's an algebra problem that I'm going to be providing a solution for. This is actually my second time recording this because the first time that I recorded this, there was no sound. So here I am doing this again. So the problem says, let G be a group and let Z of G be its center. So this is going to be notation for the center of the group. Prove or disprove the following. A, if G mod its center is cyclic, then G is abelian. B says if G mod its center is abelian, then G is abelian. So here we have a weaker condition here. And C says if G is order P squared, where P is prime, then G is abelian. So let's get started. So for A, proof, we are going to suppose that G mod its center is cyclic. And we want to show that G is abelian. Now let's recall what it means to be for a group to be cyclic. So if a group is cyclic, then that means that that there's an element in the group such that if you operate it with itself, you will end up generating the entire group. So let's go ahead and write what that looks like. So that is, so if you take the group generated by some element in the group and you keep operating with itself, you will eventually generate the entire group. And then this is for some element. So not specific, we don't know what element is doing this, but we know that it's happening. So for some element in this quotient group. So we want to show that G is abelian. So let A and B be elements in G. To show that G is abelian, we want to show that AB is equal to BA. And since we want to say something about A and B, let's go ahead and take these two elements in the quotient group. So let's take this element here, and remember, elements in this quotient group are just cosets. So let's take this element here, and let's take this element here. So both of these elements are in this quotient group here. Now, since G mod its center is cyclic, what can we say about these two elements? So since G mod its center is cyclic and it's being generated by this element here, or some element, then we can write every element in this quotient group as an integral power of this group here, or of this element here. So let's go ahead and write that out. So since it's cyclic, there exists two integers such that this element here that we took, or we're going to take, can be written as an integral power of the element that's generating the entire group. So this element can be written like this. And similarly, B, this coset here, can be written as G to the N operated with the center like this. Now remember, these elements here, these are cosets. So let's go ahead and take advantage of our properties of cosets. What can we say with these two green statements? Well, we can say that A can be written as G to the M X for some X in the center. And similarly, B can be written as G to the N, and we'll go ahead and use Y for some Y in the center. Okay, so we want to show that AB is equal to BA. We've defined A and B in terms of powers of G and elements in the center. So now let's go ahead and operate those two elements together and see what we get. So if we take AB, that's going to be equal to g to the m x and g to the n y, like this. Now, it's important to note that g to the m, all of the integral powers of g, and then x and y are all elements in G, and G is a group. So we're going to take advantage of our associativity property. So if we take a look at these two elements here, X lives in the center of G. So that means that X commutes with every element in G. And so with that, we can say that this is equal to G to the M, G to the N, X, Y. You can commute those two elements. Now here we have integral powers of G. So those are going to commute. But at the same time, X and Y are both in the center. So both of those elements are going to commute. So we actually have G to the N, G to the M, Y, X. And then you can kind of see where this is going. Similarly, Y is going to commute with G to the M to give us G to the N, Y, G to the M, X. And this is exactly BA, what we have here. So that concludes the abelian part. So we've shown that AB equals BA, so we can conclude that G is abelian. So thus, G is abelian. Okay, and this concludes part A of this proof here. Now, part B says, if G mod its center is abelian, then G is abelian. So we have a bit of a weaker condition here. That right away tells me that this statement might be false. Well, I know that it's false. I've worked out this problem. But in a situation like this where you're given a weaker condition, it's safe to start thinking about the statement being false. And in this case, instead of having to provide a proof that it's true, if you want to disprove a statement, like a for all statement just like this one, then you want to provide a counterexample to disprove the statement. So in this case, I'm going to provide a counterexample. So false, and we want to show that G is not abelian. So anytime I think about non-abelian groups, right away I start to think about the dihedral groups, and that's what we're going to use for our counterexample. So consider D8, and then we're going to consider its center as well. So the center of D8, of course, it's going to have the identity element, but it also has R squared. So in order to disprove the statement, first we need to satisfy the assumption here. So we need to find a quotient group G mod its center such that that quotient group is abelian. So we need to satisfy the abelian part. So let's consider, or let's look at D8 modded out by its center. So let's look at D8 modded out by its center. And in particular, we want to look at the order of this group. This is going to have order 4, right? Because D8 has order 8, and then its center has 2 elements. So 8 divided by 2 gives us 4. So this quotient group has order 4. And that's going to be important because up to isomorphism, there are only 2 groups of order 4. We have the integers mod 4 and then the Klein 4 group. So it's going to have to be that this quotient group is isomorphic to one or the other. So let's go ahead and write that out. So thus, this quotient group here is isomorphic to the integers mod 4, or it's isomorphic to the Klein 4 group, which we are going to denote as K4. Both of which happen to be abelian. So both of which are abelian. So here we have a quotient group, a group modded out by its center that is abelian. So we've satisfied the hypothesis part of this statement. But what's going on here is that dA itself is not abelian. So but d8 itself, so d8 is not abelian. And that's our counterexample. That disproves the statement. So thus not true. And that proves part B of this problem here. And now part C says that if G is order P squared, where P is prime, then G is abelian. Now again, here you need to determine, is this true? Then provide a proof, or if this is false, then give a counterexample. This is actually true. So for C, this is true. And before we prove this, we're going to state a theorem that's going to help us prove this statement. So the theorem says, it says, let P be prime and G be a group of order, P to the A for A greater than or equal to 1. Then the center of G is non-trivial. Then the center of G is non-trivial. This is going to be important because we are going to consider the possible orders of the center. So the center, so let's recall, the center of a group is a subgroup. So let's go ahead and write this out. The center of G is a subgroup of G. Thus, it can only have it can only have an order that divides the order of G. So if G has order P squared, the only possibilities of the center are, or for the order of the center, are P squared, P, and 1. But this statement eliminates the possibility of 1 because it says that the center is non-trivial. So it's not going to be 1. So we have two cases. It's either P squared or P. So let's write that out. So thus, the order of the center is P squared or it's P. We have two cases. In the case that it's P squared, it follows very easily actually. So if the order of the center equals P squared, well, let's think about what that's saying. So if the order of the center is P squared, the center is a subgroup of G, and G itself has order P squared. That tells us that these two groups are actually the same. So that means that the center of G is equal to exactly G. Now recall that the center of a group consists of all of the elements of the group that commute with each other. But if the center consists of all of the elements of the group, then the group itself must be abelian. So that finishes the proof, or at least the case where the order is P squared. And thus G is abelian. Now what about the other case? If the center of G has order P, then let's look at the cyclic, or the quotient group G modded by its center. So if we look at this here, this quotient group is going to have order, well, if G has order P squared and the center has order P, P squared divided by P, that's just P. So this has order P, and groups of prime order are cyclic. So thus this group is cyclic, and thus is cyclic. Let's write this out. Thus this quotient group is cyclic. But we just proved something about this statement in part A, right? If G mod its center is cyclic, then G is abelian. That's exactly what we have here. This is cyclic, thus G is abelian. And those are the only two cases we have. So indeed, in both cases, G is abelian. And that completes this proof. So I'll box this up and we're done with this proof.